We're going to be analyzing voltaic cells. In this example, a chemist designs a voltaic cell that uses two half reactions, and we're asked to calculate the standard cell potential, to write the overall balanced equation, and to write the cell notation. In these type of problems, when the only given is the standard reduction potential, then we're going to have to use those values to compare and decide which one is going to be labeled as the cathode half reaction and which one is going to be labeled as the anode half reaction. So the standard reduction potentials are going to give us a lot of information. The larger value is going to represent the cathode. So 1.065 is larger than negative 2.38. So the bromine is going to be the cathode half reaction. And the smaller value is going to be the anode half reaction. Okay, that's all of the given that we can come up with. So let's go ahead and start with our calculations. We're asked to calculate the standard cell potential. The standard cell is equal to the cathode minus the anode. I'm going to go ahead and plug in my numbers. And my final answer still has to obey the sig fig rules. And this is subtraction, so subtraction goes by the fewest decimal places. So my final answer is 3.45 volts. We want to make sure that we have 2 decimal places. Now for part B, we're asked to write the overall balanced equation for the spontaneous reaction that powers the cell. It is a spontaneous reaction when the standard cell potential is a positive number. And so this formula gave us a positive number, so that means with this formula we decided which one is going to behave as the reduction process and which one is going to behave as the oxidation process. So the magnesium was labeled as anode, so it's going to behave as oxidation. So that means I have to flip this equation to show oxidation. Cathode means reduction, so we're going to keep that reaction the way it is. All right, all we have to do now is to add these half reactions. We can cancel anything that appears on opposite ends, so the 2 electrons cancel with the 2 electrons, and we get an overall balanced equation. All right, and for part C, we're asked to write the cell notation. The cell notation has a very specific notation, and the anode has to be written on the left, the cathode has to be written on the right. We said that the magnesium half reaction is our anode, so take a look at our balanced overall equation. We started off with magnesium solid. We show a vertical line to go to magnesium 2+. Don't forget your phases. Then we have a salt bridge, and then we have bromine liquid. And because we don't have a solid in the bromine half reaction, we're going to have to use a comma to separate the 2 substances. Since we don't have a solid metal to conduct electricity, we do have to use an inert metal, and usually that is platinum. So in our cell notation, we do have to use the platinum to show that there's no solid in the cathode half reaction. Let's take a look at another example. A chemist designs a voltaic cell that uses these 2 half reactions, and we're asked to calculate the standard cell potential, to write the overall balanced equation, and to write the cell notation. So the only thing we have are the standard reduction potentials. So I'm going to take a look at both of these values. The larger value is going to represent the cathode. So 0.34 is larger than negative 2.71. So the copper is the cathode half reaction, and the sodium is the anode half reaction. All right, that's all the given that we have. So let's go ahead and start our calculations. We're asked to calculate the standard cell potential. Cell potential is equal to cathode minus anode. We're going to go ahead and plug in our numbers. And our final answer should have 2 decimal places. All right, for the second question, we're asked to write the overall balanced equation. In order for us to get a spontaneous reaction, our standard cell potential was a positive number, and we got a positive number by making sure that the copper behaves as a cathode half reaction, which is reduction. So I'm going to write it and keep it the way it is as a reduction half reaction. And the anode is my oxidation, so I have to flip that reaction. All right. In order for us to add these numbers up, our electrons have to cancel out. So in order for them to cancel out, I'm going to have to multiply the sodium half reaction by 2. So let me rewrite that. So copper stays the same. But my sodium needs to be multiplied by 2 for every part of that half reaction. Okay, now I can add, and I cancel out anything that appears on opposite ends. So the 2 electrons get canceled out. And now I can just write my overall reaction with phases. All right, for part C, we're asked to write the cell notation. The cell notation has to have the anode on the left and the cathode on the right. Sodium was labeled as our anode, so take a look at our balanced equation. That means I'm going to start with the solid sodium, vertical line going to the cation sodium. Then I'm going to have the salt bridge. And then I'm going to have the copper 2+ going to copper solid. And since we have solids in both half reactions, we don't need an inert metal. Good luck and keep practicing.